Hello and welcome to Engineering Earth. The topic of today's video is a brief review of momentum to prepare you for analyzing momentum fluxes through control volumes. Momentum is the product of mass and velocity. So I can say that, let me choose a different color here. I can say that linear momentum is equal to mass times a linear velocity. Matter that's moving is going to have momentum, and matter that is not moving, if it's at rest, is going to have a linear momentum of 0. Because momentum is the product of mass and velocity, the dimensions of momentum are therefore going to be a mass multiplied by a length per unit time. So if we're working in SI units, it might look something like a kilogram times a meter per second. If we're working in US customary units, maybe it's a pound of mass times an inch per hour, right? Because momentum integrates mass and velocity together, you could have a situation where an object with a really small mass that's moving at great speed could be equivalent in terms of momentum to a system that seems really quite different, like an object of great mass moving at a low speed. Right, so if I've got my small mass moving at great speed, and then I've got my large mass moving at a small speed, these two things could actually have equivalent momentum. We can also relate momentum to force through Newton's second law. We're most accustomed to seeing Newton's second law of motion written like this, where I've got my sum of external forces being equal to the product of a mass and an acceleration. But I can also see that this is equivalent to a time rate change in momentum of the system. So that another way of saying Newton's second law is that the sum of external forces is equal to the rate of change of linear momentum of that system of mass. And so by looking at Newton's second law in this way, we can also see that when the sum of external forces is equal to 0, that momentum isn't changing. And so we've already discussed in this class that momentum is a conservative quantity, just like mass or energy. But there are conditions to this. The sum of external force must be 0 in order for that rate of change of momentum to also be 0. So let's do an example. Application of momentum in a closed system, which, as you'll remember, means that no mass and therefore no momentum can cross our system boundary, where there are no external forces. So our sum of external forces will be 0. And let's say in this closed system that we have two bodies of unequal mass. So here are my two bodies, 1 and 2. And the mass of body number 1 is 4 kilograms, and the mass of body 2 is equal to 20 kilograms. And when time is equal to t, our two bodies are moving. Body number 1 is moving at a velocity of 30 meters per second. And at time equals t, body number 2 is at rest. So velocity is 0. Okay, after some time, so now we're at time is equal to t plus some delta t, body number 1 has collided with body number 2. And now they're moving together as one body. And we want to know what is the speed at time equals t plus delta t. So our solution here is to apply our Newton's second law as our governing equation. And we've already written that the application of Newton's second law to a situation where the sum of external forces is equal to 0, that momentum of a system isn't changing. So what that means is that momentum at time t has to be equal to momentum at time t plus delta t. So my momentum at time t is going to be the sum of momentum of my body 1 plus body 2. So I'm going to have m1 v1 plus m2 v2. Right, so that's my momentum at time t. And then my momentum at time equals t plus some delta t. Now my mass hasn't changed. The mass of my two bodies is unchanging, but now they've been combined into one body and they're moving at my unknown speed. I'll call it v3. Right, so this is my representation of momentum at time equals t plus delta t. So solving for v3, I can see that the speed at time equals t plus delta t, v3, is equal to 5 meters per second. I'm able to derive this because I know that the rate of change of momentum has to be 0 when the sum of external forces is 0. Therefore, I know that momentum has to be conserved from time t to t plus delta t. Thank you to the National Science Foundation for supporting this work. Great job reaching the end of this video, and please reward yourself with a moment of Zen. I study fluid mechanics because I love water and healthy aquatic ecosystems. Whatever your passion is, I hope it motivates your study of fluid mechanics.